Hi everyone, I'm JVacek. I'm in EC331, EC341, and EC311. So today we're going to be talking about a power management system, and more specifically an AC to DC converter. And so we're going to break this AC to DC converter up into three parts. We're going to look at the rectifier circuit on its own, the RC circuit on its own, and then we'll put it all together and look at the full rectified signal. So the rectifier on its own, it basically takes a sine wave and it takes the absolute value of that sine wave. So we know the signal is not linear, and for the reason because if you take a sine wave, you get a sine, you get a sine output, but if you take a sine plus a negative sign, which would be zero, you'd expect zero output for the rectified signal, but that's actually not the case. You get a signal with double the amplitude, but still rectified. And it also doesn't pass homogeneity, because if you passed a negative sign in, you'd expect a inverted rectified signal, but instead you'd still get the same exact rectified signal, which is basically the absolute value of the sine wave. So what is VD on? We'll go back to slide actually and look. So for a real rectifier, there's a difference of twice VD on. And where does that VD on come from? So it comes from, there's a built-in potential in a diode, and this built-in potential is within this depletion region, and the voltage source needs to overcome that built-in potential. So let's take a look on how that happens. Let's model that. So we'll model it here. We can model it. This is the charge distribution inside the Gaussian surface, or we model it with the Gaussian surface and we integrate. We get a curve like this, which represents the electric field. We integrate again and we get the voltage. And this voltage, this VD on, is equal to 2V out. And so that's actually what VD on is within a diode. So what happens the larger the voltage threshold? That voltage threshold is just VD on. So the larger the VD on, the bigger differences in amplitude you're going to have for the rectified signal. And how does this affect the power? One, the smaller the voltage threshold, the smaller the electric field across the depletion region, and the smaller the electric field, the smaller the power loss. So when we have greater voltage thresholds, we have larger electric fields and larger power losses because you have to overcome that electric field, and you're losing that power due to heat. So now let's take a look at the RC circuit. And this RC circuit is linear, and we can model this RC circuit with a linear constant coefficient differential equation. And this is the actual differential equation. I'm not going to go through the math to do it, but it does pass linearity and homogeneity. We can test homogeneity. If we built a Y2 signal, say A, Y1, and T, if we plug that into here, your A's will actually cancel and you're going to have the exact same. So yes, it is homogeneous. So now, what is the solution to this RC circuit? From that differential equation, you're going to get a homogeneous response and a particular response. And this is going to be the actual solution with the homogeneous response and the particular response. And with epsilon, it's just defined as R1 plus R2 all over R1, R2C. And this epsilon is also equal, or this 1 over epsilon is equal to the time constant tau. And we're going to confirm this response looking at it at an electromagnetics point of view. So if we have an RC circuit, the one we did in the previous slide, when you first apply a signal like U of t, it's almost infinite frequency. And at infinite frequency, a capacitor will act quote unquote like a short circuit. So that's why there's zero voltage. But then in steady state, after a long period of time, it acts as an open circuit, and it will charge exponentially with the time constant tau up to a certain point. And that time constant is the exact same as we got looking at it from a systems point of view. Now, we can use that concept of linearity to prove this same thing again. So if we had a signal U of t minus 1, we have our U of t signal going like this. This would be the expected response of U of t, and this would be the expected response of negative U of t minus 1. Now, if we add those two signals together, because we can do that with this concept of linearity, we get this signal here, it adds up, only taking the U of t output, then it basically starts subtracting these, and it starts to decrease. So that would be the expected output, and we can do that and make life really easy by using the concept of linearity. All right, now let's look at the AC to DC converter as on its own, or once we combine the RC circuit and the rectifier circuit. So basically what's going on, we can model VREC used as Vin minus 2 VD on as expected. Then we can also model VREC as Vout, this is Vout, plus IR1, the current or the voltage across R1. And this implies Vout is equal to VREC minus IR1. So as we expected before, VREC is going to follow Vin. Vin is this sine wave, and it's going to follow it with a difference of 2 VD on, just like we expect here. But that's not always going to be the case. It's not the same as the exact rectifier signal. VREC is going to go down, as we can see here, but Vout, which is this signal down here, is going to start going up. And at this amplitude difference, once VREC has hit its max peak height, there's going to be a difference between Vout and VREC as a delta of IR1. Then VREC is going to start coming down, but VREC and Vout are going to equal at some point. And when they equal, there's zero drop across R1. So that means there's no current flowing. So that means the diodes turn off right at this critical point. And VREC, it basically acts, or Vout, it basically acts as an open circuit at this point. So VREC will actually equal Vout until the diodes turn on again at this point here. And at this point here, VREC is going to follow Vin with a difference of 2 VD on, and the exact same thing will happen here again. All right, thank you for watching this video on how an AC to DC converter works.